Us. In this lecture, we will study monomorphisms and epimorphisms. But first, let us recall what we did in last lecture. So, if we consider the category set, and suppose A is an object in this category, so it is in the object class. Then any element, say X in A, this element can be identified as an arrow from a singleton, say star to A. So any element X in A, we can identify this X with an arrow from this star to A. I mean, with a function from this singleton star to A that takes this singleton star to the element X, which is in A. So it takes the star to X. So that means there is one-to-one correspondence. So if we denote this singleton by 1, we call this 1, then there is a one-to-one correspondence between the elements in set A. So we have elements in A and the arrows from the singleton set to A. So using this concept over here, we can exhibit a one-to-one correspondence between the elements in A and the arrows from the singleton to A. So this is one-to-one correspondence. So now an arrow, say we have an arrow from 1 to A. So if this is an arrow in a category where 1 is this terminal object, then we call this this arrow as the global element. So this is what we defined in last lecture. Now we want to define the monomorphisms. Let us first define what do we mean by a monomorphism. So let us consider a category A. So let A be a category. Then an arrow, say F, in category A, say from object A to object B, is a monomorphism. We call this arrow F a monomorphism if for any object T, if for any object, say T, of the category and any arrows, let us denote the arrows by X and Y from the object T to A. So if the arrow X is not equal to Y, then this should imply the composite map F composite X is not equal to F composite Y. So one can note here we have F a morphism from we have first X and arrow from T to A, then we have an arrow F from A to B. So this is the arrow, the composite map F composite X. Similarly, we have an arrow Y from T to A and an arrow from F from A to B, and this is the composite map composite arrow F composite Y. So if these two arrows are not equal, then these two arrows are also not equal. If such is the case, then we call F a monomorphism. So this is the definition of a monomorphism. We often, so this is the notation. So we often write this arrow, the monomorphism from object A to B with this arrow and this with the tail like this. So we write a monomorphism with this arrow. So to indicate F is a monomorphism. And we often call a monomorphism as a shorthand, we call them monic or mono. So a monomorphism is also called as a monic or mono. So this is a shorthand. Now, in this definition, uh, what replaces the concept of an element of A is an arbitrary arrow into A, as um, I mean, we have seen here. So if X is an element in A, then we can identify this X by an arrow from a singleton set into A, which takes this element in the singleton to the element X in A. So in this context, an arbitrary arrow A from say T to A is called a variable element. So this is remark. An arbitrary arrow say A from object T to A is from object T to A is called a variable element. A variable element of A, parameterized by T. So if we if A from T to A is a variable element of A, and suppose F is an arrow with domain A, and F is an arrow with source A. So this F has source A and it goes to some object, unknown object. Then we can compose these two maps. We can compose uh, F with A. So this is T, this is A, this is F. So this is here, this is A and this is F. So then we can compose these two arrows like this. So this composite arrow is same as F of A, because we identify an element A in A with this arrow, A from some terminal object A. So using this notation, we can rephrase the definition of a monomorphism. So this is first, second. So using this notation, we can rephrase the definition of a monomorphism. So F is a monomorphism if for any variable element if for any variable element to say x and y, which goes from object t to a, so they are the variable elements. So if x is not equal to y, then f of x is not equal to f of y, because now this f of x is same as f composite x, and this f of y is same as f composite y. So they are not the same arrows. Now we validate the claim that the morphisms in the uh, get we just want to validate that the monomorphisms in the categorical version is same as the injectivity. So we have a theorem. So in the category set, a function is injective if and only if it is a monomorphism. If and only if it is a monomorphism. So let us prove this. So suppose first that f is injective. So suppose f, which is some function say from object a to object to b. So let us assume this is injective. So one should note here, by injectivity we mean that if x is not equal to y, this implies f of x is not equal to f of y. Or using the contrapositive sense, we say if f of x is equal to f of y, this implies x is equal to y. So they are equivalent definitions. So suppose this f is an injective, and let us assume that say a and a prime be two variable elements. So they are the morphisms from t to a. B variable elements. So they are the variable elements of a, because these morphisms goes into a. Now if a is not equal to a prime, we have to prove that f composite a is not same as the morphism f composite a prime. So we want to use the definition of monomorphism to prove it. So assume a is not equal to a prime. So if this is the case, then there exists an element in T at which a and a prime they does not and they don't agree. So then there exists say T in T such that a of t is not equal to a of t prime, because we assume that A and A prime, they are not the same morphism. So there is at least one element at which A and A prime, sorry, this prime is over here, such that A at which A and A prime do not agree. So hence, so if this is the case, then F being injective, so we are going to use this definition. So we have A of t is not equal to A prime of t. So this would imply, so this implies F of A of t is not equal to F of A prime of t. So we are using the injectivity of F here. So since F is injective, so now using so this would imply, hence F composite A is not equal to F composite with A prime. The reason is that there is some point T at which these two mappers do not agree. So now let us put the converse. So conversely, suppose now F is monic. So hence F is monic. So conversely, suppose F is monic. We had to prove F is injective. So if F is monic, therefore for any global element, say x and y from 1 to a with x not equal to y, so if this is the case, therefore for any global element, uh, global elements say x and y from say object 1 to a with x not equal to y, we have then F composite x is not equal to F composite y. So we are using the definition of um, monomorphism here. So that is F of x is not equal to F of y. So using this notation over here. So these two things are same. F composite A is same as F composite A when here we have a global. So hence, so what we proved, we proved that x not equal to y implies f of x is not equal to f of y. So this would imply f is injective. Now there is one more result. So suppose we are given two arrows, say f and g, in a category A. So suppose f is an arrow from object A to B and g b an arrow from object B to C. So B arrows in a category A. So then we have, so we have the first item. So if the composite map GOF is a monomorphism, then so is F. So if the composite map G composite with F is a monomorphism, then so is F. The second item is if F and G are both monomorphisms, then so is their composition. Now let us first prove the first item. So we are going to assume that the composite map is a monomorphism. So suppose the composite map G composite with F, which is a map from object A to C. Suppose this is a monomorphism. So suppose it's a monomorphism. Now to show that F is monomorphism, to show that F is a monomorphism, uh, assume that uh, F composite X is same as F composite Y for some so these X and Y, they are arrows from D to M, and I mean they are the variable elements for some arrows X and Y from some object D into A. Now we are given that the composite map GOF is a monomorphism. So let us see what we get with this hypothesis. So G composite F composite with X, this is same as G composite with F composite X, but F composite X is same as F composite Y, so we can replace this as, so this is G composite F composite Y, so this is same as G composite F composite Y. Now G composite F is same as, G composite F is a monomorphism. So G composite, if G composite F of X is same as G composite F of Y, then X and Y have to be equal. So since G composite F is monomorphism, uh, then G composite F composite X equal to G composite F composite Y implies that X is equal to Y. So we started with this hypothesis and we ended up by showing X is equal to Y. So this proves that F is a monomorphism. So this shows that F is a monic. Let us prove the second item. Now here we are given that both F and G are monomorphisms. We have to prove their composition is monic. Now suppose F and G are monomorphisms, or monic, or monomorphisms. Therefore for any arrow, therefore for any arrows X and Y from D to A, where D is some object we have, um, so if X is not equal to Y, this would imply that F composite X is not equal to F composite Y, and So this would imply f composite x is not equal to f composite y, since f is monic. Similarly, this would imply g composite x is not equal to g composite y. I mean, let us do this. I mean, this way. So now g is given to be harmonic. So, and let us suppose this is our argument that f composite x is not equal to f composite y. So this would imply g composite f composite x is not equal to g composite f composite y, because g is given to be harmonic. So since, sorry, let us write here also g composite with f composite x and g composite with f composite y, they are not equal, since g is monic. Or, so this further implies that g composite f composite x is not equal to g composite f composite y. So this is our hypothesis, and this is what we proved. So this would imply that g composite f is monic. Hence, g composite f is monic. Now we want, uh, I mean, we want to use a dual notion of monomorphisms, um, and let us see what do we get using the dual notion of monic. So the dual notion of monic is called the epic or epimorphism. But before discussing epimorphisms, here is a small result. So let H be any morphism from the object D to I. So be a monomorphism. So this is given to be a monomorphism. So into an initial object. Here I is the initial object. Into an initial object. Then uh, we claim this H is a H is an isomorphism. So then H is an isomorphism. So let us prove this. So this is a one-line proof. So since I is the initial object, by definition there is a unique morphism, say I from I to D. So since I is the initial object, there exists a unique morphism, say this a little I from I to D. Then the composite map H composite I is a morphism from I to I. Also, we have the identity morphism 1 on I from I to I. But I being the initial object, so out of I there comes a unique morphism. So but here we have two morphisms, H composite I and the identity itself. So both are coming out of I. So I being initial, and by the uniqueness, and H composite I is same as the identity on I. So since I is the initial, we have the composite map H composite I is same as the identity on I. Now to prove this H is an isomorphism, it remains to prove that the identity, the I composite H is actually the identity on object D. So if we prove this, we are done. So by proving this, we prove that H is an isomorphism. So now it remains to prove that I composite H is same as the identity map on D. So note that now H composite I composite H. So H goes as it is. So I composite H is same as the identity on D. So one can note here H is a monomorphism. So H of something is H of something. That means this something is equal to this something. So hence I composite H is same as the identity on D, since H is uh, a monomorphism. So by proving these two claims, I composite H is identity on D, and I composite H composite I is, I mean this. So I think, yes, this is H composite I is the identity on one, and I composite H is same as identity on D. So uh, by proving these two claims, we proved that this H is an isomorphism. Now we have the dual notion of monomorphism, and that is the epimorphism. So let us define this first. So epimorphisms in a category are same as isomorphisms. Are same as, sorry, monomorphisms in the dual category. So if f from A to B is an epimorphism, this is an epimorphism if for any arrows say G and H from B to X with G not equal to H. So this should imply G composite F is not equal to G composite H. Sorry, G composite F is not equal to H composite F. Now we often write uh, this epimorphisms with double headed arrows. I mean, with this arrow to indicate F is an epimorphism. So an epimorphism is also called epic or epi. So an epimorphism is also called as epic or epi.